Have you ever wondered how a computer can do this? Today, we're gonna learn exactly how to do that. Detecting someone's hair color from an image sounds simple, right? Just find the color of the hair and you're done. But when I tried to automate that, the results were completely wrong. Sometimes the algorithm would detect a yellow from the wall as a blonde hair, and other times would pick the brown from the shirt instead of the hair. And the problem wasn't the color detection. The real problem was that the computer didn't actually know where the hair was in the image. And solving that problem turns out to be much harder than it sounds. You and I can instantly look at an image and understand where the hair is. Our brain separates the face and the backgrounds, the clothes, and the hair without thinking about it. But how does a computer understand that? How does it know which pixels belong to the hair and which ones belong to the wall, a shirt, or the background? And most importantly, how does that information get calculated? We need to understand a few things. How the computer represents the image, and how the convolution network detects the visual patterns, and why segmentation models like BisekNet are the key to solving this problem. So let's start from the beginning. How does the computer actually see an image? A computer represents an image as a grid of pixels. A pixel is a small unit of a digital image representing a single point of color in an image grid. More pixels usually means more details and sharper quality, but it also increases the file size. A computer doesn't see color the way we do. They store each pixels as a number, which are usually represented in binary. In most common format, those numbers are RGB, where each pixel is a mix of red, green, and blue intensity. For hair color though, the RGB isn't always the easiest to work with, because lightning can change those values a lot. And that's why we switch it to HSV. So hue represents the color type wheel, like an angle around the color wheel. The S is saturation, how strong or washed out the color is, and V is the value equals the brightness. For the extremes, hair shades like blonde, brown, and silver, those maps are like a more natural way how the human would describe that color. But we're getting ahead of ourselves. Before we start talking about the hair color, first we need to answer a more basic question. How does the computer even know which pixels are the hair? And that's where the convolution neural network comes in. The convolution neural networks were designed specifically for image processing. In many traditional machine learning approach, images were first flattened into a long vector of numbers. And when it happens, the model will lose the spatial structure of the image. So we will no longer understand which pixels were next to each other, making it harder to understand the image. The CNN avoids that problem. Instead of flattening the image, it keeps the pixel grid structure intact. And this is important because in the image, the relationship between neighbors' pixels matters. The edges, the shapes, the structure, and all depends on pixels being next to each other. And the core building block of the CNN is the convolution layer. And this layer is the network uses a small matrix called a filter or a kernel, and this filter slides across the image from left to right and top to bottom. At every position, the filter is multiplied by the pixels underneath it. Mathematically, the operation is called convolution. From a small patch of image, the output value is calculated as each filter on the network learns to detect a special visual pattern. During the training, the network adjusts the filter weighing to capture useful signals in the dataset. The earlier layers usually learn a simple feature, such as the edges, the lines, and the color gradients. Deeper layers combine those simple patterns into more complex structures, like texture, shapes, and object parts. And eventually, the network can recognize those objects. Mathematically, after convolution, we apply a non-linear activation function, often called as relu. This step introduces a non-linear, allowing the network to model a complex pattern instead of just a linear relationship. And the convolution layer doesn't use just one filter. Use many filters simultaneously so it can learn from different features. And if a layer has n filters, it will produce n filters maps. Those maps are then stacked together to form a three-dimensional tensor, which h is the height and w is the width and n is the number of features. And each slice of this tensor represents a different type of feature detected in the image. So you can think of these as a network building a multiple perspective of understanding what is inside the image. But let's stop and think what we actually have. Dozens of these features map are all stacked on top of each other. The network is rich with information, perhaps too much information. So how do we take all these and turn it into something that the model can actually work with? And that's where pooling comes in. Pooling reduces the spatial size of these feature maps, which helps reducing computation, reduce the number of parameters, and focus on the most important signals instead. And instead of learning from weighted like convolution layers, pooling performs a fixed mathematical operation over small regions of the feature map. One of the most common approaches is the average pooling. In average pooling, the network takes a small window of values and replaces them with the average. Okay, now that we understand how the CNNs process image, let's go back to our original problem. For the hair color, the first question was, what part of the image are we measuring? And there are three potential ways that we can work with these. First one would be classification. Classification gives one label for the whole image, blonde, brown, black, but it doesn't isolate the whole hair. The background, the clothes, the lighting can dominate the prediction. Second, the object detection. Draws a bounding box around the head and head's area, but the box still contains the face, the head, the sky, the background, so your average color can get contaminated. And third, the segmentation. It labels a pixel or mask so you can go only with the hair pixel, and that's why segmentation is the better option here. We label every pixel and we isolate the hair region, and not everything else near it. But you raise a new question. How does a network actually learn which pixels belong to the hair? This is where model segmentation architecture comes in. One of the models designed specific for this test is the BiSet net, short for bilateral segmentation networks. The BiSet net was built to solve a key trade-off in image segmentation. To correctly label pixels, a model needs two kinds of information at this time. First, the fine spatial details to detect precise edges, boundaries like individual hash rings, and a global context to understand what the object actually is. So for example, distinguishing the hair from a brown wall or shirt. Most networks struggles because improving one often hurts the other. And if you downsample the image heavily, you gain the context, but you lose the details. And if you keep at a high resolution, you prevent details, but the model struggles to understand the larger scene. The way the BiSet net solves these by splitting the problem into two parallel paths, the spatial path and the context path. The BiSet net architecture. Spatial path. The spatial path keeps the image resolution relatively high. This is the goal to prevent the fine spatial information, such as hash ring, the boundary between the hair and the skin, the small visual structures. And that usually has a few or convolution layers with the strike 2, producing a feature map 1/8 of the size of the original image. And because the resolution stays relatively high, the network retains the detailed spatial information. The context path. While the spatial path focuses on the detail, the context path focuses on understanding the scene and use a light-weighted backbone network like XPassion to understand the downsample of the image and builds a larger reception field. A larger reception field means that the model can understand the hair shape, where the hair is, where the face is, and what parts belong to the background versus the person. To further capture the global information, the network applies the global average pooling, like summarizing the entire image, and it allows the model to understand the overall context of the scene. The attention refinery model. Inside the context path, the BiSet net introduces the attention refinery model. And this model uses the global context to reweigh the important features. Mathematically, it applies the global average pooling, produce an attention vector, multiplying this vector with the feature map. And the result is that the networks focus more on the relevant semantics information. Future fusing model. At this point, the model has two very different types of information. The spatial path with the details with lower level features, and the context path with higher level semantic features. And those cannot simply be added together. So the BiSet net introduced the feature fusing model, which learns from how to combine those information properly. The fuse representation contains both the precise boundaries, the semantic understanding, and from these combination representation, the network produced a final pixel level prediction map. And the output of the network is a segmentation map. It has the width and height as the original image. Each pixel receives a label, passing y, x, 17, and which number represents a class such as background, skin, eye, mouth, and hair. Once we know exactly which pixels belong to the hair, the original problem becomes much easier. Now we can simply extract the pixel label as hair, convert them to HSV, and compute the domain color. And that gives us a more reliable estimate of a person's hair color. But the interesting part is that the hardest part here wasn't actually detecting the color. It was teaching the computer where the hair was in the first place. Once the segmentation isolates the correct pixels, the color calculation becomes almost trivial. And this pattern appears everywhere in computer vision. In self-driving cars, the system doesn't just detect the color and the shape. It first has to segment the scene, like the roads, pedestrian, traffic lights, and the vehicle. In medical imaging, doctors don't just want an algorithm to simply say tumor or not tumor. It needs the model that segments the exact region of the tumor so it can measure the size and growth. The computer first needs to understand what part of the image belongs to what object, and only then it can measure and classify it and analyze it. So in this project, detecting the hair color wasn't the real problem. It was a segmentation problem. And once we solved that, the rest became simple math. Because in machine learning, the hardest part is often not the prediction itself. It's teaching the model where to look. And if you like videos like these, follow us and leave a like below.